Hello and welcome. This is a second of what might become 3 or 4 videos about the horizon on a flat Earth. Now, what I want to do today is to look at what computer models of flat Earth and globe Earth predict in terms of the horizon and objects that we can see on the surface of the Earth. And then to compare what those models predict and what we actually observe in reality. And by doing this, we will be able to essentially eliminate one of the 2 possibilities, flat or globe. We won't be able to prove that one of these possibilities is correct. What we will be able to do is perhaps gather some more evidence in support of one or the other. One of the main reasons for doing this is to promote Walter Bislins Advanced Earth Curvature Calculator, which is the tool that I'm going to use to make this comparison. Walter's site is fantastic. It's full of lots of wonderful information, and this curvature calculator is an excellent model to use for either flat or globe Earth examples. It has a lot of functionality, and I'm not going to use anything like all of it today, but hopefully you'll see a little bit of how it works and be able to use it yourselves as well. Please check out Walter's site. It's brilliant, and anybody who has any doubt at all about the shape of the Earth really should be looking at this site. It's a very clear, it has some very clear and obvious demonstrations of how observations and reality match one or other model. Everything that he shows matches the globe model, but I'm quite sure that if flat earthers could come up with an example where the observation of reality matched a flat Earth, Walter would be more than happy to put that up and to show that that's the case. Thus far, there haven't been any. So in his calculator, it's possible to place a flat Earth model and a globe Earth model side by side. And what I've done here is to set up a situation where we have an observer height of 2 meters, 2 meters being chosen because it represents the approximate eye height or observer height for an average height person standing some centimeters, a few centimeters or a few tens of centimeters above the surface of the ocean. So on the shoreline, but standing pretty close to the ocean. I've placed a target object 10 meters tall, 1 kilometer away. And we can see that object in the distance here, but it is quite small. So we use the zoom function slider to bring that more into view in much the same way as you would do with the zoom on a camera. Now what we can see is that in both cases, the flat Earth and the globe Earth, the base of the object is visible, and the horizon passes behind the object in question. There is a slight difference in the amount of the height that the horizon goes behind the object, and with sophisticated measuring and leveling tools, we could measure these differences and be able to establish which case matched reality. So if we had set up a real situation of a 10 meter tall structure 1 kilometer away, on the surface of the water, we had sophisticated tools, we could establish whether it most matched the globe or the flat Earth. However, most people don't have that sort of equipment, so we need to do something different to give us a nice test, a nice prediction from each model. Very quickly explaining about horizons, objects on the surface of a flat Earth. So here we've got lines drawn across the surface to depict the surface. As we look out, the angle at which we see that object, or the lines in this case, becomes shallower and shallower. And so the lines appear to merge together and eventually form one single horizontal line across the portion of the screen here. There is no defined distance to this point, this line. The line continues, or the surface continues on towards infinity, or to the edge of the surface. And any object poking up from that surface should still be visible, no matter how far away it is. In the model, it will still be visible. In reality, even with very impressive zoom or a very powerful telescope, eventually objects would become invisible due to not enough light being able to be reflected from those objects towards the observer. It would be too scattered by the atmosphere. But the horizon isn't a defined distance. It extends off towards infinity. On a globe Earth, it's very different. There is this precise distance to the horizon line. Any surface beyond that line, beyond that distance, will be curving away from the observer, curving down and away from the observer, and not be visible. And any surface before that point will be curving down towards the observer and will be visible. And it's important to bear these two things in mind. Now, if we move our object to the horizon distance for these models, and we'll just slide the zoom in a little bit more so we can see clearly, what we see is that the object itself sits on a globe Earth model, sits directly on the horizon. The base of the object is exactly on the horizon. Whereas on a flat Earth, the base of the object is well below the horizon. The horizon is still cutting behind that object. So here we have a distinct difference between a globe Earth model and a flat Earth model. Now, you might argue that, or I would argue that if you see anything sitting directly on the horizon, then you have disproven the flat Earth. On a flat Earth, objects do not sit on the horizon, they sit on the surface, and the horizon must extend or be higher than, in your field of view, than the object, the base of the object concerned. We can test that out in the model. If we extend, and we're just looking at the flat Earth now, if we extend the distance out to 10 kilometers, the object is still quite clearly the base of the object below the horizon. It's on the surface, the horizon passes behind the object. 20 kilometers, and it still passes behind the base of the object. It's still passing behind the object. The object is not sitting on the horizon. 50 kilometers, and still the base of the object is sitting, it's visible and is below the level of the horizon. The horizon passes behind that object. And we're having to keep zooming in order to be able to see. But clearly, the base of the object is still below the horizon. Let's go to 100 kilometers. And still, the base of the object is below the level of the horizon. We'll go to maximum zoom on this model, and you can see the base of the object is below the horizon here. And even going out to 500 kilometers, the base of the object would be below the horizon. Now, this object we can't see because at 500 kilometers our zoom won't do enough. But if we make the object bigger, we can again see that the base of the object is just below the horizon. But now it's starting to get very close to the horizon. But we're having to go out to 500 kilometers to see that. At 100 kilometers, the object is clearly below the horizon. And we should be able to see that with sufficient magnification and zoom. So this is one example of what we would expect to see, a difference that we would expect to see between a globe and a flat Earth. If we see an object on the horizon, then we have very strong evidence that we are not on a flat Earth, and we have evidence supporting globe Earth. Furthermore, if we push the object just a bit further away, let's go to 10 kilometers. We have another difference between the globe and a flat Earth. On the flat Earth, the object base is visible, the horizon passes behind it. We can clearly see the difference in height between the base of the object and the horizon. On a globe Earth, the horizon passes in front of the object, not behind the object, but in front of the object, hiding some 2 meters or so of that object at this particular distance. So here again is another example. If we see a horizon passing in front of an object, obscuring part of that object, then we must be on, or we cannot be on a flat Earth, because that situation cannot occur on a flat Earth. And there is no distance or example where the horizon will pass in front of an object on a flat Earth, obscuring part of that object. And this really provides all the information that we need to actually go and compare with reality. But while we're here, we'll just look at what happens as the object moves further away from the observer. On a globe Earth, it gets gradually more and more of that object is hidden, whereas on a flat Earth, it still remains clearly in view from base to tip, and the horizon passes behind it. If we go to 20 kilometers, we now have a situation where the object is completely invisible on a globe Earth. It is now, the whole of the object is being hidden by the horizon. It's gone beyond the horizon, below the horizon, because it's on the surface, which is curving away from us. But on a flat Earth, the whole object is still absolutely visible. So I have a challenge for any flat earther. Can you produce an example of an object? It doesn't have to be 10 meters tall. It can be any reasonable height tall. Could be 10, 20, 30 meters tall. Whatever height you want, whatever size you want. Can you produce an example where at a distance beyond the calculated horizon for a globe Earth, the horizon passes behind that object? Likewise, for globe Earth believers, the question is, do we see the horizon passing in front of objects that are further away than the calculated distance to the horizon? So I'd like to show a few examples before we move on. Just these are quickly grabbed either from the internet or from my own computer. So here we have an example of a ship which appears to be on the horizon. Remember, it's not possible for this image to be taken on a flat Earth. This ship must be on a flat Earth. It should be the horizon passing behind the ship. The ship is sitting on the horizon. Now, I don't know the precise observer height. I don't know the precise distance from the observer that the ship is. But this observation, so this observation doesn't confirm the globe model particularly, but it does. It is an observation that is not possible on a flat Earth. Here's another example. We have a buoy that appears to be on the horizon, and a ship which is either, or boat which is either sitting on the horizon, just a little bit further away from the buoy, or perhaps part of this hull is hidden. But once again, what we do not see is the horizon passing behind the boat. It's not a very large picture. Let's make it a bit bigger. We do not see the horizon passing behind this object. And therefore this picture is also impossible on a flat Earth. Another example, I think this might be from the Metabunk site. Two different observation elevations. And we see ships again appearing to be on the horizon. The horizon is not passing behind these vessels. And here we have a ship which is closer to the camera, clearly in front of the horizon, and it does pass behind the ship. Now, this is not evidence of a flat Earth. Remember, on a globe Earth, we would expect to see this if the ship is close enough to us for the horizon in question and our given observer height. And in this case, it seemed to be indicating two different observer heights, 12 meter and a 2 meter. And so this is perfectly consistent with the globe Earth, but the fact that the horizon passes directly in front of or directly at the base of these ships indicates that it cannot be taken on a flat Earth. The horizon perhaps on this one does appear to go very slightly behind this ship, and so this one might be consistent with a flat Earth. The problem we have is that here, the ships that are further away, the horizon definitely passes in front of those ships, obscuring part of the vessel from view. So another example of an image or images that are impossible on a flat Earth. Here is one of the often used pictures of the Chicago skyline. Once again, we see the horizon here passing straight across in front of the buildings. We know we are not seeing all of the buildings because there are other examples of the Chicago skyline that have many more buildings visible. So again, this picture is impossible on a flat Earth. Again, the Chicago skyline, and now you can see clearly far more of the buildings are obscured by the horizon. And the horizon passes in front of these buildings, not behind them, in front of them. Again, an image that's impossible to take on a flat Earth. I've used this image in my previous video, but showing here a ship on the horizon and another ship which is partly obscured by the horizon. But the water horizon here does not pass behind this ship, it passes below it, showing that the ship is clearly on or just beyond the horizon. Again, impossible to take on a flat Earth. And a follow-up image to that one from a lower elevation, the horizon passing in front of this ship, obscuring part of the ship. Again, impossible to take on a flat Earth. Here is some land in the distance. This land is 50 to 60 kilometers from the observer. Observer height around about 40 to 50 feet. And again, the horizon passes in front of the land and is in fact obscuring land here. So we know the location of this clump of trees, and those of you who are familiar with this will know this is the Isle of Man that we're looking at here. And we know that the land continues for quite some distance here and is completely obscured by the horizon. If this was taken on a flat Earth, we should see the horizon coming along. We should be able to see right down to the base of this land. We should be able to see all of the land. And we should see the horizon passing behind the land itself, not in front of it. Another shot of the Isle of Man. And again, there is more land here and more land below here. Once again, the horizon passes in front of the land, not behind it. And more of the Isle of Man and some kind of buoy marker or something like that in the water here. And once again, the horizon is passing across in front of the land. The land is either sitting on the horizon, or it is a part of the land is sitting below the horizon. In fact, in this case, part of the land is sitting below the horizon. We know there should still be land visible here if the Earth was flat, but there is no land visible. So once again, an image that it is impossible to take on a flat Earth. Another example lifted from the internet. This is clearly a tall ship, but the hull and part of the masts and sails are completely hidden from view by the horizon. The horizon again passing in front of the ship, between the observer and the ship. And on a flat Earth, that is impossible. And the Toronto skyline, again, often used by flat earthers. And we see the horizon passing between ourselves and the buildings. Parts of these buildings are obscured. The Toronto, the city, extends far below this particular level, as we might see in some of these other images. Here we can see a slightly different angle, but we can see more of these buildings. But still the horizon passes in front and not behind. Taken from somewhat further away, a similar sort of shot to the previous one, but now only the taller buildings are seen and other buildings are not visible. The horizon passing in front of these buildings. Simply not possible on a flat Earth. Here is an example of, this is a similar example, but we'll go to this one first. Here is an example of Toronto showing all the other buildings. This is taken from much closer, so clearly we're getting a different perspective. And this is perfectly possible on a globe Earth, as well as being perfectly possible on a flat Earth, because we are closer to the object that we're looking at, then we do not see the horizon cutting through the object. It is to a large extent we're seeing down to the very base of the objects here, almost to the shoreline. And I think maybe one last one again showing a similar thing. We can see to the shoreline, we can see ships here, but we are close to Toronto, and therefore we see all of it, just as you would expect on a globe Earth and on a flat Earth. But the problem is that when you look on a go further away and look at what you can see, the horizon now is obscuring large parts of the Toronto skyline. And that is what is impossible on a flat Earth. So I'm making that assertion, but I'm making that assertion based on the predictions from modeling accurately a flat Earth and a globe Earth, and asking what we should see in both cases. And what we should see on a flat Earth is the horizon passing behind the object, and we should be able always to see the whole of the object. If we can see the top part, we should be able to see the bottom part. And so here's the challenge to flat earthers. Produce an image in reality that actually matches what a flat Earth model predicts for objects at or beyond the distance to the horizon if the Earth were a globe. If you can do that, then you will have some evidence to support your flat Earth theory. I have never seen an image like that. I've never seen an image that comes close to being like that. And therefore, we can discount a flat Earth as our explanation. It is possible that there is an alternative to the globe Earth model. And flat earthers quite like to try and find small discrepancies between the amount of an object that is hidden by the horizon in reality and what the models actually predict. And they point to these small discrepancies or apparent discrepancies, in their eyes discrepancies, and claim that they therefore have proof that the globe is false. This is quite absurd and is easily explained as part of the globe model. Any apparent discrepancies are easy to explain. And I will make a second challenge to flat earthers. Produce an example where the relevant data can be verified. That is the observer height, the target distance, and the target size, which does not fit with what we expect to be able to see on a globe. And if you can produce an example of that, then I will happily try and place that into Walter's curvature calculator and see what the prediction of the globe actually is. If you can come up with something which we can verify and which proves to be impossible to model correctly on the globe, then I will concede that you have now got an example which completely disproves the globe model, and therefore we must discard that globe model as it stands for a refined version or a completely different model. To date, I have not seen such an example. Every single example of discrepancies between the globe Earth model and what we observe in reality turn out to be easily explained by getting accurate observer height, accurate target distance, accurate target size, and incorporating a small amount of or a acceptable amount of refraction to explain the observation. Now, flat earthers might be unhappy with the use of refraction, but refraction in the atmosphere is a phenomena that can be observed and even measured, and can be and should be taken into account when using the globe Earth, applying the globe Earth model to observations. And I may talk about refraction a little bit more in the next video. But that's it for today. Hopefully that's not too long. And I look forward to seeing some really excellent examples from flat earthers of evidence in the real world that actually agrees with the model shown here, or evidence that does not agree with the globe model.